next speaker is Tamar Ziegler. Tamar's early work on characteristic factors, Furstenberg averages, and null flows are closely connected to Gowers norms, and her joint work with Green and Tao on the inverse Gowers norm problem led to a complete generalization of Vinogradov's theorem concerning, he dealt with one linear equation in three prime unknowns, and they generalized this to any system of rank 2, meaning if you have two more variables than equations and it's not degenerate, you can always solve the equations in primes if there isn't a local obstruction. Quite a remarkable achievement. Most recently, Ziegler and Tao have given a polynomial generalization, namely something of the following type. Suppose you want to make suppose you're given k polynomials, p1 up to pk, in one variable, and you want to make n plus pj times m, where n and m are variables, prime simultaneously. Then this can be done unless there's, so it's again two free variables, but a nonlinear version, as long as the one variable is appearing linearly. I should say that I think 15 years ago, such results could not be dreamt that anybody could prove such a theorem. It would have looked to, I think, most experts much more difficult than the twin prime, for example. And today these are now coming out of a very powerful machine based on null factors and things like that. So her talk today is, I think, on this topic, concatenating cubic structures. Thank you.
Okay. Okay. Yeah, so it is working. So it's a great pleasure and honor to be here at a conference honoring Jean's work. So what I'm going to talk about today is not directly related to Jean's work, but I do want to take the opportunity to say something about his earlier work that had impact on me as a grad student. I think maybe the second research paper I read as a grad student was a paper of Bourgain's. I was interested in questions about configurations and subsets of positive density in Euclidean space, and Jean had this really nice result saying that any such set contains all large distances. And later on, I was interested in questions regarding multiple averages that are connected to Samoraides' theorem. So these are multiple ergodic averages, and for the applications, one is interested in the L2 convergence of these averages, but they raise very natural questions regarding pointwise convergence of these types of ergodic averages. And I think the state of the art today is still Jean's work from some 30 years ago about convergence of the averages corresponding to t and t squared. So maybe the reason nobody's talking about it now is that there's no serious advance since. Anyway, so this is right. So what I want to talk about today is this question of polynomial progressions in primes. So this is a question that I was got interested in when I was here at the Institute as a postdoc some 10 years ago. And actually, I share Alex's experience of being terrified of Jean. So I think I didn't exchange maybe a sentence or two with him when I was a postdoc here. And only later, when I grew up, or I don't know, I got more confidence, then I found out that he's actually very nice and very generous with his time. And so I kind of regret not having that confidence while I was here for a year. And anyway, that's it. So I want to talk about this concatenation of cubic structure. Okay, so Peter introduced this, but I'll state the problem again. So suppose we're given a system of k polynomials and r variables in integer coefficients, so p1 through pk, and we want to ask the question, well, maybe we want to have all p1m and through pk prime, but that I can't say anything about now. So instead, I ask the question about a polynomial progression. So I look at x plus p1 of m through x plus pk of m, and we ask ourselves, can we make all of them prime simultaneously, and if so, how often? Okay, so old conjectures say that this should happen we can have them all all the collection of x plus pi m all prime infinitely often if and only if there is no local obstruction, there's no some divisibility problem. So, for example, I can't make x plus 2 and x plus 4 prime infinitely often because one of them will be divisible by 3, but except for these type of divisibility problems, then this should happen. Yeah, so this is no local obstruction, so no trivial divisibility condition problem. Okay, so the conjecture also gives asymptotics for how many such configurations we expect to find in some box of size n. Right, so in a series of papers by Green-Tao and one last one by Green-Tao and myself, we prove that this conjecture is true if the degrees of all the polynomials all polynomials are linear, so the degree is smaller or equal than 1, but actually the degrees of all the distances are exactly 1. So we can't have, for example, x and x plus 2 because the degree of the difference is 0. But anything else we can have and also obtain asymptotics for such. So, for example, into this category falls the problem of finding arithmetic progressions. If I want to find arithmetic progressions, just finding arithmetic progressions in the primes, this is the well-known Green-Tao theorem. But if you want to count how many there are, then in a box of size n, then this would fall within this theorem. So it's very natural to try to generalize this to the question of polynomial progressions. So when the degrees are greater or equal than 1, and this is the result I want to talk about today. So what can we say if the PIs are not linear? And this is the recent theorem with tau. So the conjecture is true if the degrees of all polynomials are smaller or equal than d, and also the degrees of the differences are exactly d. Okay, so we would want the degrees of the differences maybe not to be exactly d, and surely this should be true, but this is what our methods can give, and you'll see why the fact that the degree of the differences exactly d is important for this. Okay, so we can do this, and so the conjecture is true. So we can have these prime infinitely often if and only if there are no local obstructions, and similarly asymptotics, but asymptotics in the sort of maximal range of the parameters. So here's an example. So for example, if I'm looking at this first triple x plus n squared and x plus 2n squared plus n plus 4, then the natural, if x is in the ranges up to n, then the natural range that n should go to, the largest range that makes sense that n can go to is square root n. So we can do this if n ranges to its maximal range, which is square root n. And similarly, we can look at the second configuration, x plus nm plus nk, nm plus nk. And I want to fix on this example because I can demonstrate most of what happens through this specific example. So this is going to be our working example. I'm going to try to explain the difficulties in trying to, there's all the machinery that we developed to understand linear polynomials. And I want to try to explain what is the difficulty in going from linear to polynomial. So the working example I'm going to take is this configuration, x plus nm, x plus nk, and x plus nm plus nk, where I take nm and k ranging to their maximal value, which is square root n. And so as the first thing one would try to compare it to is a simpler average, so a simpler configuration. So if I'm looking just at x plus u, x plus v, and x plus u plus v, and I take all parameters ranging to their maximal values. I take every u, v, and x. They're all of size n. So the whole thing is the range of the parameters. That's the problem. Okay, and that's the name of the game here. So this is what we're going to try to understand the difficulty and how to overcome it. So if we're looking at the second configuration where u and v are large, so they're the same scale as x, then if I'm trying to find configurations of the second type in some in some subset, then it's dominated by then the behavior is dominated by the Fourier analysis. So if you take a function f, I can think of my interval between 1 and n as I can identify it with z mod nz, and maybe I have some overlaps, but I don't really care. And I try to understand configurations of the second form. Then if I look at there's a simple computation. So this notation over here, this notation is an average. So when I write the parameters underneath, I'm just averaging over the range. So this is, in this case, it would be 1 over n cubed of whatever sum of x, u, and v ranging up to n. So it's a simple computation to see that if I'm trying to evaluate the expression, so the expression f of x plus u, x plus v, and x plus u plus v for the function f, then it's simply exactly equal to the sum of to the L4 norm of the Fourier transform. And so and this is dominated by, so if my function is bounded, L2 bounded, then this is dominated by the largest Fourier coefficient. Okay? So what is this? This is what I mean by this expression is dominated by, or it can be explained by Fourier analysis. And the way one can use this type of information is, suppose you're looking for this type of configuration in some subset A, then you would be looking at the characteristic function of the set 1A and trying to evaluate if I try to evaluate the left-hand side average, this is simply the count of such configurations inside A. So I count how many such configurations, and if my set A has all its Fourier coefficients small except for the trivial coefficient, then my set behaves like a random set of size A. Then the number of such configurations I have is like the density of A to the 4th, or something like that. Okay, it's as if I would flip a coin and ask whether an element is inside A with probability that is the size of A. Okay, so this second case, when all parameters range up to n, is very well understood. Okay. So what's the problem? And well, the problem is that if you try to run this argument for the first expression, for the first quadruple of with your parameters ranging up to only up to square root n, then at least naively it doesn't work. Okay, you don't get a nice expression. There's not sufficiently good cancellation in the expression. So this is the problem we want to try to overcome. Before that, let me just explain a variant of this question. Suppose that we're looking at the same type of averages, but now I don't have my example is where I have this product of n times m, n times k, and n times m plus k. But suppose I don't have this situation, but I'm just looking at mk and m plus k, but all the parameters range in some short range. So x is large, and I'm looking at all the other parameters range in a range of some interval h. So I can think of, say, h as square root n. Then I want to explain to you why this is difficult even in the easiest case. So here's a baby case. Suppose you're not interested in this quadruple, but just in two, x plus m, and I think of m as ranging up to square root n, or up to some value h. Then if I try to evaluate the same type of average, so I'm looking at an average of f of x and f of x plus m, then this is more or less the same as I can make a local shift. I can shift in the short variable, and this is roughly the same as looking at the average of x up to n and the average of m up to h of f of x plus m squared. Okay, and just to demonstrate that this is already a difficult question. So the problem is that at these short scales, we don't understand interesting functions or arithmetic functions that we would be interested in. So for example, here's a classical result. This is the Möbius function that I actually will show the definition of in the next slide. But if I take the Möbius function and I want to evaluate its long range averages up to n, then it is equivalent to the prime number theorem that there's cancellation, so this is little o of 1. However, if I actually want to evaluate this type of average that I have over here, so I'm chopping it up, I'm looking at I'm looking at these shifted averages in short intervals. So I look at the averages over short intervals and average over that, then it's a very recent breakthrough of Matomaki and Radziwill. I don't know if I'm pronouncing his name right. That actually, if I plug in the Möbius function for this expression over here, then then I have cancellation when h goes to infinity as slowly as I want. I should mention how big a breakthrough this is. Before this result was known unconditionally, I think only for h of size n to the 1/6 plus epsilon or something like that. So even in this very baby case, there's only very recent breakthroughs. So it's a problem to try to, if we want to understand the primes or the Möbius function or any arithmetic function, it's a problem if you want to understand things at short scale. Okay? Okay. Right. So, but here is the problem. So back to this non-baby case problem. So how could you try to attack it? Well, you could try to use Fourier analysis to have kind of local control. So what does local control mean? I can make a local shift and look at these same typical type of averages and think of them as many averages of the type that I already know how to understand, but at intervals of range of size h. Okay, so I can have control. I can have a kind of understanding with local Fourier coefficients. So if I think of my function, I fix this h and I look at fx of y. Fxh of y is f of x plus y, then I can think of this function as a function on z mod hz. So I fix this interval h, and I can try to say, okay, I already know how to understand the previous averages when all parameters are of the same range. So I will have local control with the Fourier coefficient. So I have local control of this function f hat. And the problem is, then I need to understand these kind of short scale behavior of Fourier coefficients for nice functions I'm interested in. I already showed you that this is a non-trivial question even for the trivial coefficient, okay, not just for the supremum over the Fourier coefficients. So here is so what would I want from in order to analyze the previous question? Then here's the definition of the Möbius function. So maybe for those of you who haven't seen it, so this is the function that takes -1 to the k if n is the product of k primes, distinct primes, and 0 otherwise. Then here is what we would conjecture that would be true if I'm trying. So inside over here, I have the supremum of the Fourier coefficient of mu thought of as a function on a short interval starting from x. So I look at the interval from x to x plus h. I try to analyze the Fourier transform there, and I would conjecture that that if I average this over all starting points, then I should get cancellations. So if you delete the supremum here and put alpha equals 0 here, then this is the same as the Matomaki Radziwill result. Okay. So if we could get something like this, then, which we don't even know for h equals square root n, let alone h going to infinity as slowly as I want, then we could get an average, we can get an estimate of this type. So if we knew this, we could get this type of estimate, but we don't, and this is not the way I want to.
In your case, h will always be good enough if h was a small power, right, always. But all your polynomial range.
No, well, it will be, the case I can attack is only if both n and m go up to exactly square root n. I can't, the product needs to go into some, I need n times the scale of n and the scale of m to be the scale that you know something about, okay? You'll see this in a minute. So here is back to the problem that we can try to attack. So why can we attack this specific problem when we do have this extra n that comes. So I'm looking at nm, nk, and nm plus k. So what is the advantage there? Well, I can try to think of this in the following way. I can try to think of it as if I had, so suppose I fix two integers, n1 and n2, and I look at this, progression n1 times m. This is a progression of size h, of size square root n over here. And I look at these progression for k and progression for h. So I think of these as sort of two subgroups of z mod nz. So they're not exactly subgroups, but I think of them as subgroups of z mod nz. And I know that if n and 1 and n2 are sufficiently prime one with respect to the other, then k and h are independent subgroups in the sense that if I look at the sum of them, then k plus h covers a positive density of integers between 1 and n. So I think of this as k plus h is of order n. Okay, so this is greater than a constant times n, and each point I can get to each point of bounded multiplicity. So I think of this as some maybe with some weighted n, weighted interval n. But for me, this is the same as n. So I think of this k and h, k plus h with this property. I think of them as the full n. Okay. So if I think of it this way, then this is the way I want to think of these averages I'm looking at. If I fix this subgroup k, I can look at averages along, kind of cubic averages along the k direction. So I fix x. I look at x plus k1, x plus k2, and x plus k1 plus k2. So this is a cube in the k direction. And I have a cube in the h direction, x plus h1, x plus h2, and x plus h1 plus h2. So a two-dimensional cube in this direction, and two-dimensional cube in the h direction and in the k direction. And ideally is, or the key question or the key thing we want to do is can we somehow concatenate this information, the information in the k direction and the h direction, to get information in the k plus h direction? Or this brings me from local square root n behavior in one direction and local square root n behavior in an independent direction to a global behavior of scale n, which I understand I worked very hard to understand. Okay. Okay. So here's kind of a general question you can ask. So suppose you have some abelian group G and you have two subgroups H and K. So they don't have to be exactly subgroups, but let's say subgroups H and K. And we're given information about some a-dimensional cubical average along H. So I had 2 dimensions before, but I could generalize this to any dimension I want. So instead of having U, V, the parallel pipette generated by U and V, I can have this any dimension that I want. So I have an a-dimension cubic average along one subgroup, and I have a b-dimension cubic average along another direction. And I ask, can I say something about cubic averages with respect to the sum of the groups, H1 plus H plus K? So here's a notation I want to use. So we denote by delta HF. This is going to be the discrete derivative of f in direction h. So fix an element h in the group h, and I can differentiate f, multiplicatively differentiate f in direction h. So I look at f of x plus h. Well, I want to multiply by f of x inverse, but it's more convenient to conjugate. So I look at f of x plus h times f of x bar, and I think of this as a discrete derivative in direction h, okay, for some element h in the group h. And for example, if I do this twice, if I differentiate with respect to h and then with respect to k, then I get something that looks like a cubic average. And if this 2-dimensional parallel pipette, which is exactly the configurations I was looking for before. So if I do this many times, I would get a times I would get an a-dimensional cube. And I'll call a function f an h polynomial of degree smaller than m. If I take consecutive m derivatives, then I annihilate. Okay, so if I discretely differentiate in direction h1 through hk for all elements h1 through hk, then this is trivial. So here's an example. Suppose your group G is z squared, and you're looking, one subgroup is the x coordinate, and the other one is the y coordinate. So I have these groups h and k, and I can look at this function f of xy, which is e of xy alpha. Then if I fix y and differentiate, if I just differentiate along the x coordinate, then this is a linear function. So it's a polynomial of degree 2 in direction h. And similarly, if I fix the x coordinate, differentiate with respect to the k group, with respect to the y coordinate, I also get a linear polynomial. But if I try to differentiate with respect to the whole group with h plus k, then not in G. So in G, it's going to be a polynomial, a 2-degree polynomial. If I discretely differentiate this function, well, you see, it's a quadratic polynomial in xy. So obviously, I can't expect something better than this. And here's a rather simple statement. So suppose I have two subgroups of a finite abelian group, and the simple fact is, if I have my function f is an h polynomial of degree smaller than a in one direction, with respect to the group h, and a b degree polynomial with respect to the subgroup k, then it's a h plus k polynomial of degree smaller than a plus b minus 1 with respect to the sum of the groups. Okay, this is very easy. It's like the proof is generally the same as proving that if a composition of two polynomials, a polynomial of degree m and a polynomial of degree n is a polynomial of degree m plus n, and it's almost the same in this situation over here. But here is a slightly harder fact. So suppose you're not trying to solve this problem, and you don't know this information for all cubes, but you only know this information for almost all cubes. Okay? Then, so you know that f looks like a polynomial on 1 minus delta proportion of the h cubes, and it looks like a polynomial for 1 minus delta proportion of the k cubes. Can I say, is it close to a polynomial with respect to, of the right degree with respect to h plus k? And one can generalize arguments of Alon, Kaufman, Krivilevich, Litzin, and Ron to say that that's true. Okay? And the point is that if you're close to, there's only one polynomial you can be close to. So you can try to guess which this polynomial is. If you know that you look like a polynomial for many cubes, then you can ask the cubes what, if you're given a two-dimensional cube, you can ask your cubic friends what you think your value should be, and that would give you the polynomial you're looking for. So you can get a polynomial of degree a plus b minus 1. The polynomial, you're close to a polynomial of the right degree. But the question that we need is much harder, and it says that suppose you're given information on only a small proportion of the cubes. So I'm not assuming. So there are three categories. There's an algebraic category when all the equations hold, and then you can try to solve that. Sometimes this could be hard or easy, but this is one. Then you can have the almost all categories. So you know that your condition holds almost everywhere. Are you close to something that looks really algebraic? And then you have the last category, which is which you only know, only have this very partial information. You only know that you look like a polynomial or I don't know if you look like a polynomial. You only know that this condition holds for very small but non-trivial number of cubes. Can you still say something interesting about your function? There's kind of a general philosophy you can apply to many problems. So this is what we assume. So suppose you know that your function looks like a polynomial in the delta proportion of the h cubes and delta proportions of the k cube and of the right degrees a and b. So this is already interesting in the case 1 and 1. Okay, so degree 2 and degree 1 polynomial and degree 1 polynomial in so a equals 2 and b equals 2. That corresponds to linear polynomials in both directions. And so how can you quantify this? Well, there's this gadget of the Gowers norms where you look at all these derivatives, so d delta, so you fix your subgroup H, and you fix A, which is the degree you're interested in, and you look at these, you average over all such cubes, and if this is 1 on delta proportion of the cubes, then this is going to be positive, or this is going to be delta. Okay? So I have Gowers norms. This would be a Gower norm in direction H with respect to the subgroup H. And now, okay, so what is the difficulty with this, with the problem that we have in the 1% world, where you only know this information on a small proportion of cubes? Well, one difficulty is that you have no uniqueness. So if your function is a sum of polynomials, well, these are polynomials multiplicatively. So if a function is a sum of polynomials, then it's not a polynomial. A sum of polynomials is not a polynomial. A product is. Okay, so this is not a polynomial. So if you are a sum of a few polynomials, then you would have this condition hold. So you'd have your H Gowers norm greater than bounded away from 0. But there's no unique choice of you guessing what should be. And the second difficulty, it has to do with the first one, is that if you know that your Gowers norm is bounded away from 0, this doesn't necessarily imply that your function f correlates with a true polynomial. So we have this. So in the 1%, in the 99% world, you know that if you're almost on, if you're 1 on almost all cubes, then you're close to a polynomial. But if you're bounded away from, if you're bounded away from, if you're look like a polynomial in only a positive proportion of cubes, then it's not necessarily true that you even correlate with a true polynomial, with an H polynomial. Even in the case when your H is the same subgroup as G. So you're looking at G, H equals G, and you're looking at these Gowers type norm for H equals G, then and G is the group Z mod n Z, then the inverse theorem for the Gowers norms tells you that you correlate not with an a-1 degree polynomial, but actually with an a-1 degree step nil sequence, which is a more complicated object than a polynomial. So these are genuinely different than true polynomials. So these are the two kind of key difficulties when you're in the 1% world, when you only know very partial information. And so ideally, what we would want to be able to say is that suppose you have you have non-trivial Gowers norm in the H direction. So you have this degeneracy. Well, maybe not exactly this, but something that quantifies this in direction H, and you have the same thing in direction K. Then you correlate. Then your function has UH plus K, A plus B minus 1 norm greater, bounded away from 0. Okay, so the way you should think of it is what you would want is this: if you have kind of nil behavior in direction and short intervals in one direction, and you have nil behavior in another direction, then you have nil behavior and maybe higher step in the sum of for the sum of the subgroups. Okay. So let me give you an ergodic analog of this question. It's easier to formulate what one can do and see the results here. So suppose you have so you can ask the same type of questions in the ergodic world. So suppose you have a countable abelian group, and you're looking at a measure-preserving system. So you have x b mu, that's a probability measure space, and you have a bunch of transformation TG, which are measure-preserving transformations, and you have some subgroup H of G, and you can also differentiate in the ergodic category. So you can take a function f, a bounded function, and look at the discrete derivative or I don't know how the ergodic derivative in direction H. That would be looking at f of thx, applying thx and multiplying by f of x inverse. By the conjugate of f of x. And similarly, you can define an H polynomial. So an H polynomial would be something that annihilates after H steps. So for example, if you're looking at a function whose second derivative is 0 or annihilates as 1 is simply an eigenfunction for the action. Okay, so these would be kind of generalized eigenfunctions, functions satisfying this condition. And again, you can make the same kind of definition, so you can kind of quantify, you can look at all these derivatives in the in directions h1, consecutive derivatives in directions h1 through hk. And instead of summing over x, now you integrate over your measure space, so the sum over x turns into the integral over integral d mu. And you take some limits, or you take some growing sequence in your group. So this, say a Fourier sequence in your group H, and you look at this limit, and it's you can in the case when of measure preserving systems, these are called Host-Krag-Gowers norms. So these were defined for measure preserving systems for z actions by Host and Krag. And you can, by kind of general nonsense, deduce that you can classify the behavior of these norms by, there is a unique factor of the system. So there's a unique morphism from x to a unique factor zhax, so that the condition that the Gowers norm, the Gowers Host-Krag norm is 0 if and only if you're orthogonal to this factor. Okay, so there is a factor that captures the entire behavior of these averages. Regardless, you don't need to understand the structure. Just the existence of this factor follows from kind of general nonsense. And the question that you want to ask in this ergodic situation is given two subgroups, H and G, and can we relate this? So this factor, we call it kind of the characteristic factor for the average. So it characterizes the behavior of the average. And we want to ask, can we relate the characteristic factor for the H action and the characteristic factor for the K action to the characteristic function for the sum of for H plus G action? And maybe I should remark that this question is interesting if the action of H and the action of K are both ergodic, which means that the action of G is ergodic as well, then this question becomes very easy because all these characteristic factors are shared. So they're the same for the characteristic factors for H, and the characteristic factor for G are for an ergodic subgroup are the same. So this question becomes interesting if you have some degeneracy. So you have these two subgroups and they don't act ergodically. So there's no easy way to connect the behavior in one direction and in the other direction. And what we can show is that the intersection between them, so if you have a function that is measurable both with respect to one factor and with respect to the other factor, then it is measurable with respect to the correct factor z h plus k with respect to and the a plus b minus 1. Okay. So what does this imply for our Gowers norm question? Well, recall that the condition that these factors, these characteristic factors, the h, they exactly classify when these Gowers norms are 0. So you got to be slightly careful that it doesn't quite mean that if you have non-trivial, so this would tell you this condition over here, or the condition that you have non-trivial Gowers norm in the h direction, a non-trivial Gowers norm in the k direction, tells you that you have non-trivial projection onto one factor and non-trivial projection on the second factor. But it doesn't tell you that you have non-trivial projection on the intersection of the two factors. So you can't quite get this, but if you have many such subgroups, if you have a collection hi of such subgroups satisfying this condition, then you can get that for many pairs, I and J, you have the right the result you're interested in. Okay, so you have a large Gowers norm in the direction of the sum of the groups. So so how do we apply it to our situation? So here's the application. Not yet, sorry, here's almost the application. So now, after describing what we can get in the ergodic statement, then I can explain easily what we can get in the combinatorial one, then if G is a finite abelian group, say Z mod n Z, and you have two subgroups, so they don't have to be exactly subgroups like the ones we had before, which were kind of inflated intervals, then so ideally, again, we would want this. This is what we wanted, so we can't always get what we want, but we can almost get what we want. So if we have a collection of such subgroups, we have many of them, then we have the condition we're interested in. So for many of the sums hi plus hj, and how can we apply this? So here's how we apply this to our situation. So this is, I didn't write the original average, but this is the average we're interested in. So if I differentiate in direction nk and then differentiate in direction mk, this is exactly gives me the sum of x plus nm, x plus nk, x plus nm plus nk. That was the working example. So over here is a kind of a shorter expression of this thing. So what I have here is, so think of these for any fixed n, you can look at these subgroups, nm, so these are subgroups of size square root n, okay, almost subgroups of size square root n, and I have lots of them for many pairs n1 and n2, so not for many pairs n1 and n2, n1 and n2 are sufficiently independent so that the sum of these hn1 plus hn2 is comparable to n. This is why we need the parameters, so we can get the maximal range of the product of the parameters. So this is the average we were looking at, is the average over here, and this exactly says so. So what can we deduce from that? If our function has small u3 norm, so 3 is 2 plus 2 minus 1, so a equals 2, b equals 2, and 2 plus 2 minus 1 is 3. So if my function looks, if my function has small u3 norms, this is kind of in the contra, instead of greater than, this is in the application, this is more useful. So if my function has small u3 norm, then in many directions, for many n, well, not for many n, if in the other direction, if I had many n's for which this average was bounded away for 0, then I would have many subgroups for which the average is bounded away from 0, so many sums for which it's bounded away from 0, so I would get that the Gowers u3 norm is large. So in this direction, it says that if the Gowers norm is small, then these averages that I'm interested are small. And as an example, for the Möbius function, the fact that the Möbius function has small u3, global u3 norm, now I'm allowed to use scale n. At scale n, we understand the behavior of the Möbius function, and this specific result, that the fact that the Möbius function has a small u3 norm is a result of Green and Tau. Actually, they have a result that this is true for any k. So for any uk, the Gowers norm of the Möbius function is small, then this average for the Möbius function is small. So this we automatically get from this type of from this corollary. So but we want to apply this for primes actually, and not for the Möbius function. And the entire discussion was for bounded functions. Functions taking values in the unit disk or in minus 1, 1. So, well, which is not something we can apply to. Normally, if you want to understand functions, questions about primes, we need to look at the Fourier function, which is not bounded. It takes value log p for prime p. And so you need to use this transference machinery that was developed by Green and Tau for proving Semirates' theorem for the primes to transfer this result to the primes. But actually, it's not entirely straightforward. And one needs to use both the simplifications due to Conlon, Fox, and Zhao. And actually, inside the transference principle, one needs to use the concatenation result again. So it turned out not to be at all straightforward to transfer this result to make it work for non-bounded functions or functions bounded by a pseudorandom function. And once you do that, then you are at scale n. You need to use the entire machinery that was developed for understanding primes, linear equations and primes at scale n. So it uses all the machinery. This is on top of the entire machinery that was developed before. It just brings the problem. If the parameters range to their maximal value, then we can as I described before, then we can bring the problem to a scale n problem which we understand. And here's another thing we can show is that if we use the inverse theorem for the Gowers norm, we can show that in this corollary up here, we can actually replace U3 by U2. For those of you who well, I didn't explain I didn't show exactly what the U2 norm, although you saw it in the expressions before. But this means that actually these expressions that I have over here are dominated by the Fourier behavior. And I don't know how to do this directly. So the only way I can prove this result is going up to the U3 norm and then going back to the U2. And it seems like a challenge for Fourier analyst people to try to, so it's true, so to try to prove that these type of averages are actually dominated by the largest Fourier coefficient of the function, and I don't know how to do this directly. Right, and maybe one last remark is one can use this concatenation technique to get polynomial progressions in primes with a very short gap. So if I'm not interested in asymptotics and I'm not interested in non-homogeneous polynomials, so I'm only looking at homogeneous polynomials and I don't care about the degrees, then one can get polynomial progressions with as small as gap of power of log n, where this power depends only on the collection of polynomials and not on anything else. So